Hello YouTube. In this video we're going to introduce the law of sines, and this is a law that we use in trigonometry to solve typically oblique triangles. It applies to right triangles. It's just that right triangle math we use a lot of sine, cosine, tangent, SOHCAHTOA, and once we hop out of right triangles we tend to not be able to use our common trig ratios. So what we have is a couple of tools at our disposal, the first one being the law of sines. Okay, so we say first things first, let's introduce ourselves to the law. And that is this. We say, first of all, let's let there exist a triangle ABC, and what we'll say is that the vertices of the triangle are A, B, and C, and also I want to explicitly state that A, the measure of angle A, is less than the measure of angle B, is less than the measure of angle C. So we could clearly state that C is the largest angle on the triangle. So I think that this is really important before we go ahead and do an example, that we go ahead and start by practicing how would you necessarily sketch this situation. And you're going to have to forgive my triangle here. But here's my oblique triangle. And what we're saying is that C is the largest angle on the triangle. So we tend to use a capital C on our vertices, or a capital letter on our vertices. So we say C. Furthermore, we could label the other two vertices. It's ambiguous in this instance, but I'm going to say that since A is the smallest angle, we're going to put it over here. We say A. And then B, excuse me, it's an intermediate angle. We could put it that way. It is the case that when we label triangles, we tend to give C the largest vertex, but also this. When you label the side lengths, we'll use the same letters but lowercase, and we'll also put the letter of the side opposite the letter of the angle. So that is, if this is angle C up here, we'll call this side opposite lowercase c. If this is angle A over here, we'll call this lowercase a. And then if this is angle B over here, we'll call this lowercase b across from it. This is very important, as a matter of fact, that we realize one thing, and this is a property from geometry, but we say if A is less than B is less than C, and we're talking about the angles here, we say angles, then it is the case that the side lengths also follow the same scheme. And this kind of, if you think about it, is reasonable in that, of course, the longest side is opposite the largest angle, and the smallest side, A, is opposite the shortest angle, or the smallest angle, okay, least amount of rotation. So that being said, it kind of leads us to this law of sines over here, and here it is, the law of sines. It says this: if you were to take the sine of angle A, which is our smallest angle, and divide by the side length opposite A, so the smallest side length, that is the same exact ratio value as if you took the sine of angle B, which is our intermediate angle, divided by the length of its side opposite, which is lowercase b, and you get the same thing as if you took sine C divided by C. I think it's worth mentioning at this point that we also say the law of sines can be expressed as the reciprocal of all three of these original ratios here. So we say A over sine A is B over sine B is C over sine C. So this, of the two laws that we deal with, law of sines, law of cosines, this one is the most convenient to remember. Okay. So let's talk about its use and its convenience. Okay. So the law of sines. Law of sines, maybe we'll just go ahead and start by kind of setting up an example here. We say, well, I want to solve the triangle. Now, solve the triangle for which the following things are true. Solve the triangle means I want to know everything about this triangle. That is, I want to know all three side lengths. I want to know all three angle measurements. Okay, and units are important here. So what if we were given specific information, excuse me, and you notice up top here I write the two angles in one side case. What if we already had known that A, the measure of angle A, is 30 degrees, and the measure of angle B, for the sake of convenience, we'll go with like a simple angle here. We say 70 degrees. And we also get kicked out of side length. How about we go with side length A? And I like the metric system here. So we say A is 8 centimeters. The most important thing is that we start by sketching the triangle that goes with this here. So it's not drawn to scale, but we can say this. We'd say, okay, so what do we know about this triangle? We know that angle A is 30 degrees. We know that angle B is 70 degrees, and side length A is 8 centimeters. Now our goal here is to solve this oblique triangle, this non-right triangle. Let's be more general about it here. So we say, okay, if we know first of all that angle A is 30 degrees and angle B is 70 degrees, the nice thing about starting with the two angle case is this: we can always determine the third angle because we know that the sum of these three angles must be 180 degrees. That is, if we were to determine angle C, we could say the measure of angle C is actually equal to this: 180 minus the measurements of the other two angles. Oops. So minus that, minus this. We could take 30 degrees off of our 180 and 70 degrees off our 180 because we know that all these angles add up to a sum of 180 in the first place. So we say the measure of angle C would be 180 minus these other 100 degrees. It leaves us with 80 degrees. So already we've got that C is equal to 180 degrees, or excuse me, 80 degrees, and we want to go fill this in as the moment we determine this. Okay, so we have 30, 70, and 80. Now, here's where the law of sines comes in. We have to determine B and C. Now, let's imagine we actually knew, say, B. We know A and B. First of all, we could not use the Pythagorean theorem here because this is not a right triangle. So we'd have to rely upon something like the law of sines. But we do not know, we know neither B nor C. So what we're going to do is, first of all, we're going to pick a side for which we'd like to determine the length. And so I'm going to go with B. I want to know B. Now, the law of sines, as we saw over here on the left, says we're setting up ratios of angles and side lengths opposite. So what we're going to do is we're going to set up a proportion, okay? And recall a proportion is something to the effect of A over B equals C over D from geometry. And what we'd like to do is set this up so that there's one unknown thing. And that unknown thing here is going to be B. And also this, since we're setting these up with angles and sides opposite, we're going to look for angle side pairs. So maybe it would be helpful if I switched colors here. We'll switch over to like a magenta or something like that. You'll notice that we know angle A and we know angle, or lowercase a, or side length A. This is what we're looking for. So we can set up a primary ratio here. So we could say right off the bat, I'm going to say this. We say 8 centimeters, which is our length of A, over the sine of angle A. So we have A, really A, over sine A. Okay. So now, since we're solving for B, we say B is our unknown side length. We're going to put this over the sine of B, but you notice that we know angle B here, we say, is 70 degrees. So now that we've got this proportion set up, all we need to do is solve this proportion. So recall that with proportions, I'll take you back over here on the left. If we had a proportion A is to B as C is to D, there are a few routes we can take here, but the most common route I see people taking is that if two ratios are equal, then we say that their cross products are equal. So that is AD would have to be the same value as BC. Let's go ahead and work with the cross product method or approach here. We say, okay, so 8 times sine of 70, we get 8 centimeters times sine of 70. So 8 times sine of 70 degrees, which would be this primary cross product here on the main diagonal, is equal to side length B times sine of 30 degrees. So this is B times sine of 30 degrees. So now, to isolate our B, we'll divide both sides by the sine of 30 degrees. So sine of 30 degrees. And so now, this is all going to be calculator work from here on out. We can just type these things into our calculator because we say this is the value of B right here. So if you wrote this on your paper, I'd say, hey, bravo or brava, you've actually got the answer, but we want a reasonable number. So let's go ahead and go over to our calculator here. We said 8 sine 70 divided by sine 30. So we have 8 times sine 70. So first of all, our numerator comes out to be this value, 7.515, 75. We're going to take this divided by the sine of 30. Sine of 30 degrees, mind you. And we end up with a value that is approximately 15. We'll go about 15.0. I want to keep that 0. We say B, lowercase b. Let's write this in here. Lowercase b is, approximately, what did we have? We had 15.0. So approximately 15.0, and we were measuring this in centimeters. And so like earlier when we discovered C, we went and filled it in. Let's go ahead and go up here and we'll fill in B. A few reasons why we'll do this, as a matter of fact. One, we're solving this triangle. We want to determine all of the measurements or metrics on this, but also to determine reasonability. And I noticed that B is 15 centimeters long. That's opposite a 70-degree angle. Okay, so I think that's reasonable given that A was 8 centimeters and opposite a 30-degree angle. 70 is a little bit more than twice the measure of 30 degrees, and so we have a side length that's reasonable here. The other thing we can say about this is, well, C, lowercase c being the longest side length, it's got to be a little bit bigger than about 15 centimeters. So we're going to do the law of sines again, but this time we're going to solve for C. We want C. So again, let's set up an angle side pair, and my number one recommendation is this. When we use the law of sines, let's go ahead and use the same ratio we began with. That was, we said side length A, which was 8 centimeters, over the sine of A, which was 30 degrees, is equal to, now we're dealing with C, we say lowercase c over sine of C. and we have in this instance, that's the sine of 80 degrees. So now again, running a cross product on this, we say, okay, so sine 80 times 8, or 8 of these sine 80 things, 80 degrees, is equal to c times sine of 30 degrees. And so now we can split these both by sine of 30, sine 30 degrees, sine 30 degrees. And we get c is approximately, so we'll take 8 times sine 80 divided by sine 30. So we have 8 times sine 80, enter, divided by sine of 30 degrees, enter. And we run out with approximately 15.7 or 15.75. So we'll call it 15.6. So we say C is approximately 15.6, and we're measuring in centimeters. And we're going to go fill this in, and again, just to determine a measure of reasonability. And this is entirely reasonable. It's very close to our angle side, our side length B, but you'll notice that the angle B and angle C were also very, very, very close. So this is a quick example of how you would run through using the law of sines to solve a triangle in a 2-angle and 1-side case.